Hello class, welcome to the lesson for today. We are talking about sound like we did in our last lesson. In the previous lesson, we did define what sound is, what type of a wave it is. We did discuss about a few more terms that are related to sound. For example, echo, velocity, frequency. And then we did look at the 4 properties of sound waves, which are common to all other waves. We had a few worked examples, mathematical examples, to show how we can calculate the speed of sound, frequency of sound, and the period. In our lesson today, we'll describe more about sound waves. We'll look again at the properties of sound waves. We'll talk about a few applications of sound, and then we'll have more worked examples to help us to understand the concept. So by the end of this lesson, we should understand that sound waves are longitudinal waves which can be reflected, can be refracted, and can be diffracted. Then we should know the frequency range for human hearing, which is between 20 Hz to 20,000 Hz. Describe how to measure the speed of sound in air. So like we said, sound is a wave that is produced by vibrating objects. In our last class, we did look at how we can vibrate the 2 palms, bring them together, and they produce a sound like a clap. Or, in the case of half-meter rule, hitting it against the table, and you produce sound because it will vibrate when it hits the table, as such. Sound waves is a mechanical wave that has vibrations which occurs in air and other substances. Sound can be transmitted through solids. So sound is a longitudinal wave where the energy travels in the same direction as the particles through which the sound vibrates in, but the particles move back and forth, parallel to the direction of wave travel, back and forth. So for example, that is a longitudinal wave in the red arrow. That is the direction that it takes from this point to that point. The particles through which the sound wave is moving will move back and forth as shown by the blue arrow in this case. So, here's a further illustration to show how sound will move through a solid like such. Now through air, or through material, through air, sound wave consists of a series of what we call compressions and rarefactions. Compressions will be places where the molecule of the medium are closer to each other. Rarefactions where the molecules of the medium are far from each other. So for example, we put the sound loudspeaker to give out the sound. What will happen is there will be regions where the particles of air are close to each other, like here, that will be the compressions, and then there will be regions where the particles of air will be very far from each other, like here, and that's what we call the rarefactions. So a compression is a region of slightly higher pressure, where the air molecules are closer together than usual. Rarefaction is the opposite, where the particles of air are far apart from each other than will be expected. Now wavelength is a distance covered by one wave. In the case of sound wave here, wavelength of the sound is equal to the distance between 2 successive crests, 2 successive compressions or 2 successive rarefactions. Like you can see in the diagram here, this is a region where molecules of air are closely pressurized, they are together, that's one compression. Then you have a large region of rarefaction where the molecules of air are far apart, and then the next one where the molecules of air are closer together, that's another compression. So the wavelength will be the distance between 2 successive compressions in this case, and that's what we call the wavelength of this particular sound. Now here's a diagram which is expressing the same thing. A loudspeaker giving out that sound in the case of compressions and rarefactions, leading to the air molecules between the speaker and the ear being compressed together to form what we call compressions, these ones, which appear like vertical lines, and then will be regions where molecules of air are far apart with less pressure, here, 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 and here. So you end up having a series of crests and troughs, as you can see on the diagram below here. The C represents the crests, the R represents the rarefactions. A continuous arrangement like this, which can be portrayed on cathode ray oscilloscope, to be a wave with crests and troughs. So in this case, the crests representing the compressions, the trough representing the rarefactions. And the sound wave will be transmitted from the source to the ear, which can perceive it and interpret the words depending on the particular human being. So what is the range of hearing? Humans can perceive sound which is produced from a range of 20 Hz to 20,000 Hz, depending on the pitch and loudness of the particular sound. But of course, biologically, age can damage and reduce the upper limit that one can perceive this. So for example, an old person or someone exposed to prolonged high volume may no longer be able to perceive or hear sounds above 10,000 Hz, because this one interferes with the, or because age interferes with the hearing or the efficiency of different parts of the body. Some animals can hear much higher frequencies, and this is where all of us know that the dog is much more efficient as a security animal. Birds and dolphins can perceive sound of up to 100,000 Hz. 100,000 Hz. Now there's a picture of a dolphin. Dolphins are said to be able to perceive that kind of sound from a very long distance, and that's why they can come very quickly to rescue someone who is stranded at sea. Dogs, on the other hand, can perceive sound of between 40,000 Hz to 60,000 Hz, of course depending on the breed of the dog. And that's why, because they can perceive this kind of sound, which is much higher than what human beings can perceive, they are very good to be used as security animals to detect the presence of an intruder. Now these are a few photographs showing different organisms, of course producing different kind of sounds. We have dolphins here in water who can produce their own sound, communicating and also perceive. This is just a cartoon illustration of a dog and a cat fighting. Of course they don't speak, but that's how it can come out. That's a picture of two friendly animals, a dog and a kitten. Now here, we have a picture of an icon, Nelson Mandela speaking to a child. These are various examples of where sound is used, whether it is in human beings here or in animals to detect or communicate in water and in different other scenarios. Now, there are two more terms which are associated with sound: ultrasound and infrasound. These are two different types of sound depending on the frequency. Ultrasound is a high frequency sound which is above 20,000 Hz. That's too high to be heard by humans. Ultrasound echoes can be used to measure distances such as sonar and to see the inside of objects, or what we call scan. Here we have a very good diagram of a sonar sounder which is used by fishermen not only to perceive the depth of the water body in which they are, but also to detect the presence of fish. Now one fish may not be very easily noticed, but a shoal of fish, a collection of them can be very easily noticed by this sonar sounder, and that enables fishermen to know where to cast their nets and fish. Okay, we can also use this kind of sound to come up with what's called scanning devices. Scanning can be used to detect what is inside a body without doing any surgery. X-rays, like we did see in our previous topic, can be used to detect the presence of hard solids like bones. But scans like this can be used to detect the presence of soft tissue. For example, growth of cancer cells, or more often than not, the presence of a fetus in the womb. That is ultrasound. Infrasound is a low frequency sound which is also inaudible to humans, although you may feel the presence of some vibration. For example, infrasound is kind of the sound that is produced by earthquake waves before the earthquake comes on the surface of the earth. So earthquake waves are in the form of infrasound, and with special devices can be perceived before an earthquake occurs. Also, elephants and some other large animals can be able to detect infrasound. And that's why you probably heard that before earthquakes occurs in places, before tsunamis occur in places, some animals will move from the danger area because they can perceive the very low frequency sound that come about from earthquakes before it actually hits the earth. Now, sound waves in different materials. We say that sound waves travel fastest in solids. For example, a train can be heard approaching through the rails over a long distance before it actually appears. Sounds travel well through liquids, and that's why whales and other water animals like the dolphin can be able to communicate over great distances while in water. But sound travels slowest in gases. The speed of sound, of course, increases with temperature in gases. However, sound does not travel completely through vacuum because there's nothing there. The reason why it travels fastest in solids is because molecules of solid are closely packed to each other, they vibrate and can transmit energy. For liquids, it's a bit further apart, but for specialized or adapted animals like whales and dolphins, they can communicate over that. Air is much more difficult because the molecules are farthest apart. In vacuum, it's impossible because there's nothing in vacuum to allow vibration to be transmitted. Now that brings us to the end of the first part of our lesson. In the coming part, in the second part of our lesson, we'll have more of the same. See you.